A student prepared cyclohexene by heating cyclohexanol with concentrated phosphoric acid. The cyclohexene produced was distilled off from the reaction mixture. So cyclohexanol is going to be heated to produce cyclohexene. The concentrated phosphoric acid is just a catalyst. We're going to be dehydrating via elimination to make cyclohexene. It says complete the diagram of the apparatus used to distill the cyclohexene from the reaction mixture at 83 degrees. 83 degrees must be the boiling point of cyclohexene, or around about the boiling point of cyclohexene, so that's what comes off. So if we're looking at it at the moment, we can see that they've put the mixture in a flask. We've got the distillate, the cyclohexene, coming over to the conical flask. At the moment, if we were to heat this, all the vapours would escape through the top. So we do need to put a bung in the top, and we need to put a bung in the top, but we also need to be able to measure the temperature. So let's put a thermometer in, and the thermometer bulb needs to be level with the side arm. So we want to put that thermometer in. Let's label that thermometer level with the side arm. And then we need to put a bung in, not cutting through the thermometer. Okay, so we've sealed the flask and we've put a thermometer in. Now, as the vapours pass into this tube, we can see that there's no condenser jacket on that tube. So we need to add a condenser jacket. Remember that the water in and the water out needs to be in the right places. So water in at a lower level, water out at a higher level. So we'll label our condenser. This would be full of water. The water's coming in near the bottom of the condenser and out at the higher level, nearer to the flask. And then we've labelled and completed the diagram. The distillate, which is this part here, was shaken with saturated sodium chloride solution. The cyclohexene was separated from the aqueous solution using a separating funnel. State why cyclohexene can be separated using a separating funnel, and that would be because the two liquids are immiscible. The cyclohexene and the aqueous layer, they don't mix. So it's not just that they have different densities, it's that they don't mix. Cyclohexene separated in question 2.2 was obtained as a cloudy liquid. The student dried this by adding anhydrous calcium chloride and allowing the mixture to stand. Give one observation that the student made to confirm it was dry. The liquid goes clear, is no longer cloudy, and that means that the water droplets have been removed from our cyclohexene. In this preparation, the student added an excess of concentrated phosphoric acid to 14.4 grams of cyclohexanol. So let's do that bit first. Let's work out how many moles of cyclohexanol we used. So 14.4 over 100, which would be you can use your calculator for this, 0.144 moles. So the theoretical, because it was a 1-to-1 reaction, so the theoretical moles of cyclohexene would be the same. How much did we actually make? Actual moles of cyclohexene. Well, we made 4.15 centimetres cubed with a density of 0.1810 grams per centimetre cubed. So if we multiply those two together, we'll get the mass, because it's 0.81 grams per centimetre cubed and we've got 4.15 centimetres cubed. And if we divide the mass by the MR, we'll get the moles. So if we do that on our calculator, then we see that the top number would be 3.36, and then we're going to divide that by 82. And if we divide 3.36 by 82, we get 0.0410 moles. So our actual over theoretical for our percentage yield, so 0.0410 over 0.4 as a percentage, so times by 100 is 28.5%, because we're going to give it to 3 significant figures because it asks for the appropriate significant figures. So we're rounding it to 28.5%. Then we've got the next part of the question, asks us to complete the mechanism for the reaction of cyclohexene with bromine. So we're going to go from the pi bond to the delta plus bromine, which would be the one closest. What that's going to do is open up the pi bond and put a Br onto one of the 2 carbons. The other carbon will then become a carbocation, and when we broke the Br-Br bond, we made a bromide ion with a lone pair, and then that's going to attack that carbocation, and we're going to get our 1,2-dibromo cyclohexane.